Okay, so you know how we're always trying to figure out the brain?
Yeah.
Well, this time we're diving deep into something super cool
Oh,
called harmonic brain modes.
oh, very interesting.
Yeah, and it's basically this new way of looking at how our brains work across different mental states.
Yeah. So like whether you're awake or you're asleep or, maybe even under anesthesia or something like that.
Right, exactly.
We're going to look at all that.
Yeah, so it's all about linking up the brain's structure, its function, and even our subjective experience.
Like how we experience the world, how we feel,
Yeah, how we feel, what we're thinking.
all of that.
Right. And our main source for this deep dive is a paper called,
Ooh, a preprint
yeah,
from Biorcaf
sure.
Harmonic Brain Modes, a unifying framework for linking space and time in brain dynamics.
Yeah, it's a long one
That is a mouthful.
by Silanadesoy and a whole team of really smart researchers.
That's right.
And basically, our goal today is to kind of unpack this concept of harmonic brain modes and see how it helps us understand.
The relationship between brain activity and different states of consciousness.
Right. And like you were saying, all those different states, wakefulness, sleep anesthesia, psychedelic experiences,
Absolutely.
and ultimately how all of this connects the space of our brain.
The actual physical structure, the
Yeah.
networks,
The networks and the time.
the oscillations, the rhythm.
Rhythms, right?
Exactly.
So it's kind of bringing it all together.
It's that space-time link that's really fascinating.
So, in neuroscience, one of the biggest challenges has always been to figure out how the brain's anatomy, the actual physical structure, is linked to how it functions, and then how that relates to consciousness.
Right. It's like this huge puzzle
A huge
with
puzzle.
all these different pieces.
And we're trying to see how they all fit together.
Exactly.
Yeah.
And for a long time, one of the key pieces we've been looking at is brain oscillations.
Right. The brain waves.
Yeah, those electrical pulses that happen at different frequencies
And we see those frequencies change.
all the time.
Yeah, depending on what you're doing.
Right, like if you're super focused,
You have those higher frequency
you get the beta waves going,
beta waves.
and then you drift off to sleep, and
Everything slows down.
much slower delta waves come in.
Right. It's like this whole spectrum.
It is a spectrum.
But it's not just about the frequency itself.
No, it's more complex than that.
Right. There's more to the story.
There's more to the story. And then there's this amazing discovery about a decade ago.
Yeah. What was that?
Resting state networks, or RSNs,
So basically, when your brain is just kind of chilling out.
seemingly doing nothing.
Yeah, but it's actually not doing nothing.
It's still active.
There's all this activity going
These
on.
organized patterns of activity
Mhm.
between different brain areas.
Like it's never truly off.
It's never truly off.
It's always doing something.
And what blew everyone's mind was that these RSNs looked a lot like the networks that are active when you're actually doing things.
Like when you're focused on a task.
Exactly, like when you're seeing or moving or thinking.
No, it's almost like the brain has these default settings.
Like these pre-wired teams ready to go.
Even when you're just daydreaming.
Exactly, even when you're just zoning out.
Which is so wild.
It is wild.
But then it gets even more interesting.
Oh, tell me more.
Because these RSNs, these networks we think are for specific tasks, are actually present in all sorts of situations.
Not just when we're awake.
Right, not just when we're awake. We
We
see them in light sleep.
Oh, wow.
And even under anesthesia.
So when consciousness is supposedly absent or very low,
Yeah, it's like, are these networks really linked to consciousness?
it's a paradox.
It is a paradox.
If they're there even when we're not conscious,
That's their role.
and that's exactly where harmonic brain modes come in.
Okay, so explain this.
This is the attempt to solve this puzzle.
Yeah.
The researchers suggest these harmonic brain modes are like the fundamental building blocks of brain activity.
Okay, so like the basic ingredients?
Yeah, like imagine you're making a complex dish.
Okay.
You have all these different ingredients.
Spices and herbs and...
Yeah, exactly. And they combine to create something delicious and complex.
Right.
Well, harmonic brain modes are like those fundamental ingredients.
Of brain activity.
Brain activity. They're the foundation.
Okay, I'm following.
Good. So what exactly are these harmonic brain modes?
Yeah, what are they?
They're defined as harmonic modes of structural connectivity.
Catchy.
I know, right? But they also call them connectome harmonics,
Connectome harmonics.
which is a bit cooler.
Yeah, a little bit cooler.
But the key here is this definition links the physical wiring of your brain.
The connectome.
The connectome to the rhythmic activity, the oscillations.
So it's saying that the way your brain is structured physically actually influences the types of rhythms it can produce?
Precisely. It's like saying the shape of a drum influences the sounds it can make.
Oh, that's a good analogy.
Right, so that's the bridge between space and time in the brain.
That makes sense.
And this paper explores this idea across 4 main mental states.
Okay, hit me with them.
Normal wakefulness, just like we are now. Psychedelic states, those altered experiences. The
Interesting.
different stages of sleep, including REM and NREM sleep.
So dreaming and deep sleep.
Exactly. And then the unconscious state of anesthesia.
So pretty wide range.
It covers a lot of ground, and it's important to remember that consciousness itself is defined as having a stream of personal and subjective experiences,
Right, your own unique experience of the world.
which can obviously change dramatically depending on the mental
Yeah,
stuff.
definitely now we know that brain waves change in these different states.
Oh yeah, their speed and intensity fluctuate all the time.
So how do these harmonic brain modes relate to those oscillations, the time aspect?
So we've known for a while that brainwave frequencies change with different mental states.
Like alpha waves decrease and delta waves increase during sleep.
Exactly, or how anesthesia can mess with alpha activity.
Right.
And psychedelics often reduce alpha too.
So it's not just the frequency itself.
No, it's the overall patterns, the spatiotemporal patterns that matter.
How those rhythms are spread out across the brain.
Precisely, it's the whole picture, not just the individual frequencies.
Okay, so that's the time side. What about the space, the network activity?
Ah, yes, the RSNs we talked about.
How do harmonic brain modes help us understand what's going on with those networks in different states?
So RSNs show us the spatial patterns of brain activity.
Right, like which areas are firing together.
Exactly, and the default mode network, or DMN, is a classic example.
The one that's active when you're daydreaming.
Yeah, when you're thinking about yourself, not focused on the outside world.
And we see that even when people are under anesthesia or in light sleep, right?
Right, which was a puzzle.
A big one.
But what we've learned is that the connections and organization within those networks change a lot during those states.
So even if the network is active, it's not functioning the same way.
Exactly. It's like the parts are there, but the communication is different.
Can you give me an example?
Sure. In deeper sleep,
Yeah.
under anesthesia, the connection between the prefrontal cortex and the rest of the DMN weakens.
The prefrontal cortex, that's like the CEO of the brain, right?
It's involved in planning, decision-making, higher-level thinking.
So it's like the CEO is off duty.
In a way, yeah, it's less connected to the rest of the network.
Interesting. And what about psychedelics? How is that different?
They seem to have kind of the opposite effect.
Oh, really?
We see a decrease in connectivity within the DMN.
So the internal communication is reduced.
Right, especially between the front and back regions. But at the same time,
There's more communication between different networks.
exactly, like the DMN might start chatting more with networks that are usually active during focused tasks.
So it's like breaking down barriers between different parts of the brain.
In a way, yes, and with LSD, we even see an overall increase in connectivity across the whole brain.
Wow, so everything's talking to everything else.
More or less, yeah. And what's really cool is studies have shown that under psychedelics, people have a wider variety of functional connectivity patterns.
So more diverse network configurations.
Exactly, suggesting their brains are exploring a wider range of possibilities.
It's like the brain is getting more creative with its connections.
You could say that, and the idea is that this richness, this flexibility might be a key signature of different mental states.
That's fascinating.
It is.
So it's not just about which areas are active, but how they're interacting.
And how that communication changes in different states.
Right now, let's zoom in even further
To the microscopic level,
to the level of individual neurons and their signals.
the neurophysiology.
What's happening there with the excitatory and inhibitory signals in these different states?
And how do harmonic brain modes fit into all of that? Okay, so at the most basic level, brain activity is all about a balance between excitation and inhibition.
The gas pedal and the brakes.
Exactly. Signals that make neurons more likely to fire,
The excitatory one.
often involving the chemical glutamate.
And those that make them less likely to fire.
The inhibitory ones often involving GABA.
And the connectome, the physical wiring of the brain, acts as the infrastructure for these signals.
The roads and highways they travel on.
So when we lose consciousness, like in sleep or under anesthesia,
There seems to be a shift towards more inhibition or less excitation.
like the brakes are being pumped.
In a sense, yeah. And on the other hand, psychedelic states might involve increased excitation,
So more gas pedal.
potentially through the action of serotonin on specific receptors.
Okay, so we've got these shifts in signaling. How do harmonic brain modes tie this all together?
Well, the paper suggests that all this neural activity, the oscillations, the network dynamics, can be understood as different combinations of these harmonic brain modes.
The connectome harmonics.
Exactly.
So it's like the brain has this set of fundamental vibrational patterns.
Based on its structure.
And the balance of excitation and inhibition determines which patterns are active at any given time.
Precisely.
I remember you mentioned a musical analogy earlier.
Oh, yes, like a guitar string.
Can you explain that a bit more?
Sure, so imagine a guitar string vibrating.
Okay.
It doesn't just vibrate at one frequency.
It can create different harmonics?
Exactly, those overtones that give the sound its richness.
And you can even see these vibrations as patterns on a plate covered in sand.
Those are called Chladni figures.
Right.
And even the behavior of electrons in atoms shows harmonic patterns.
So it's a fundamental principle in nature.
It seems to be, and mathematically these patterns are described by equations that link the shape of the vibrating object to the frequencies it produces.
So the structure dictates the possible frequencies.
In a way, yes.
So these connectome harmonics are like the brain's natural resonant frequencies based on its physical structure.
That's a great way to put it. They're the brain's inherent vibrational patterns.
And each harmonic corresponds to a specific frequency and a synchronized activity pattern across different brain regions.
Like each harmonic is a fundamental note that the brain's structure can play.
And those notes combine to create the complex symphony of brain activity.
That's a beautiful analogy.
And these harmonics, they just emerge naturally from the interplay of excitation and inhibition in the brain.
That's what computer models suggest.
It's like the brain is a self-tuning instrument.
Constantly adjusting its harmonies.
That's amazing.
It is. And so how does this all relate to the different mental states we experience?
Yeah, that's the big question.
The key is that changes in the overall balance of excitation and inhibition act like a conductor.
Guiding the orchestra.
Exactly. They determine which combination of these harmonic brain modes are active at any given time.
So it's like turning the volume up or down on different sections of the orchestra?
You could say that, and this shift in the active modes then leads to the different patterns of neural activity we see in different states of consciousness.
Can you give us some specific examples?
Sure. So when we lose consciousness, like in deep sleep or under anesthesia, there's a decrease in overall excitation or an increase in inhibition.
Like we talked about earlier.
Exactly. And this leads to a narrower range of harmonic modes being active, mostly the low-frequency ones.
Which explains the slower brain waves we see, like delta waves.
And also that decoupling we talked about between the prefrontal cortex and the DMN.
Because the higher frequency modes that support that integration are less dominant.
Right. So it's not just that brain activity slows down.
It's that the repertoire of active harmonic patterns becomes restricted.
It's like the orchestra is playing a simpler, more repetitive tune with fewer instruments.
And what about the psychedelic experience? How does that fit in?
In psychedelic states, where there's evidence of increased excitation, the model suggests that a wider range of harmonic modes become active.
So the orchestra gets bigger and more instruments come into play.
Exactly. This broader range of
Yeah.
active modes leads to the increased variability in brain signals and the altered connectivity patterns we see.
It's like the brain is exploring a wider range of its inherent harmonic possibilities.
Precisely, it's able to play a wider range of notes and create more complex melodies.
So it's like consciousness is this rich symphony with all these different notes, these harmonic modes playing together in this intricate way.
And loss of consciousness is like a simpler, more repetitive tune with fewer instruments.
That's such a powerful image.
It is a striking contrast.
So to bring it all back to our listeners, what are the key takeaways about this harmonic brain mode framework?
Well, the big picture is that it gives us a completely new way to think about how brain structure and the principles of harmonic waves can explain the diverse patterns of brain activity we observe.
Across different states of consciousness.
Exactly. It offers a potential link between the neural oscillations and networks, where the brain's anatomy.
And maybe even hints at the how of our subjective experiences.
It's a step towards understanding the underlying mechanisms of consciousness.
And what makes this framework so exciting for the future of brain research?
It provides us with new tools to analyze brain activity.
By looking at it through this lens of harmonic modes.
We might be able to understand the fundamental mechanisms that drive different states of consciousness much better.
Potentially leading to new ways to understand and address various brain conditions.
Exactly. It's like having a new language to decode the brain's complex activity.
It makes you wonder how these fundamental principles might apply to other complex systems too.
Absolutely. And that brings us to our final thought for our listeners today.
Ooh, I like these final thoughts.
Consider how this idea of harmonic activity, this interplay of fundamental building blocks, might relate to other complex systems you encounter in the world.
Like social networks or ecosystems.
Exactly. Or even weather patterns.
Yeah.
How might the balance of excitation and inhibition be a fundamental principle in many areas beyond just our brains.
It's like a universal principle of organization.
Perhaps, and on a deeper level, maybe ponder how disruptions to these fundamental harmonic patterns within the brain could be linked to different neurological or psychiatric conditions.
It's a whole new way of thinking about the brain and its connection to the world around us.
It's a fascinating avenue for future exploration.
It really is food for thought.
Definitely food for thought.
Thanks for diving deep with us today.
Always a pleasure.
We'll see you next time for another deep dive into the fascinating world of science
Until then, keep those brains buzzing.
and those harmonic modes humming.
Thanks.